Okay, so an ISA is a list of things that a computer can do. What does that mean? We we talked about how an exe, you give an exe or you let an exe take over your computer. With specifically the CPU, you let it run whatever it needs to run, and then yeah, that's you running code on your computer. An ISA is, well, the instructions that that exe can run. For example, if you are writing assembly, which is just a high-level version of machine code, which you can read, so it's just readable machine code basically. If you're reading that and you use add in a certain way, like you want to add in a particular way, you have to go or you have to adhere to however your ISA requires that you add, right? You have to adhere to that. And I'll show you examples in a moment, but first, let's talk about some fundamental stuff. Opcodes, or instructions, are split into opcodes and operands. Okay? Opcode is what you want to do. You can imagine it being like this. One is add, two is subtract, etc. Right? And then operands. Operands are what you're going to do, or what you're going to add with, right? Am I going to add RIX, which is what is called a register? A register is the fastest form of memory in your CPU. So we've been talking about like a RAM and disk. RAM and disk are outside of your CPU, but these registers are in your CPU, right? Mm-hmm. Okay. Now, yeah. So let's talk about the three major ISAs that you'll probably have to deal with. You might not have to deal with all of them, but you're probably not going to deal with anything else, right? Those are x86, ARM64, and RISC-V. Okay, so an x86 label looks like, or x86 assembly looks like this, right? It has a move instruction, which I don't think is seen too much anywhere else. I don't think that is. I don't know. Maybe there's a macro, but move is, I'm pretty sure, exclusive to x86, and a couple other things are exclusive. But let's talk about some things that are similar, right? You'll see this thing called a label, right? x86 underscore label. What that label does is it points out an instruction, and points out an instruction that you can jump back to. Now let's elaborate on that, right? Say this is a little bit of this is just a code section in RAM. This is the code section. It's the code section, okay? You look at this. This is instruction 1. It's instruction 2, instruction 3, instruction 4, instruction 5, right? Let's say we have a label here, right? This one's a label. There's a label over it. My bad. So there will be some instructions say add REX1 or something, right? There will be a label. And then let's say there's a jump here. Okay. So whenever we hit this jump, we would go down. We would go hit line number 1, 2, 3, 4, 5, and then we would jump back to here. So our code would go back to number 2, right? That's what a label does. It is just a piece of the code section that we specify that we can jump to, and we specify we can jump to. A common example of using a label is to do if statements, or the assembly version of if statements, right? So yeah. Hmm? All right. Another thing we have to look at, besides RBX, which we've talked about, is this address plus 1. What is address plus 1? Address is a memory location, right? Plus 1 adds a single byte to it. Hmm? And then these brackets. What do these brackets do? These brackets say I want the contents of the memory location. Let's say we want a pointer. We can do that. And then we get the pointer. Okay. So we can move and we do a compare. Compare is like your if statement. Once again, compare your value to 2, and then we jump if it's equal to. If it's not equal to, we go on. But if it's equal to, we go back here, and this one executes again. Right, that's it. All right. ARM label. ARM is slightly different. Notice that add RP. What is RP? Add, I believe, a relative page address. Right? What is a relative page address? You take your program counter. We talked about, or we haven't talked about. The program counter is what keeps track of what your line you're on, right? So if we're executing 1, 2, 3, 4, 5, if we're on line 3, the PC will say the program counter will be line 3, and it'll move on to line 4, then it'll move on to line 5, right? So it just keeps track of what we're actually executing. Mm-hmm. Okay, what the page address does is it takes the page address given by the program counter, right? From the program counter. And let's assume that this is 20 bytes, or 20 bits, sorry. Right? So 20 bits, and then this full thing is 32 bits. At least I believe. It might be 64, I'm forgetting. Right? And then the second one. What is the second one? It's adding x9 is equal to, so say x9 is equal to, or this new value of x9 is equal to whatever x9 is plus the bottom 12 bits, right? X9 plus bottom 12 bits, which is a load 12 of address, right? And that's how you get a virtual address. So ARM makes you build your own virtual address. Now that we've built our own virtual address, the operating system on its own will convert that to a physical address. But we don't have to do anything because we've already built our virtual address. Now that we've built it, we can load our value plus 8, right? Plus 8 bits. All right, we load that value plus 8 bits into x1. We compare that to the value 2, right? Is x1 equal to 2? If it is, branch. If it isn't, move on and we load x1 plus 16, and we add this further. RISC-V, okay. RISC-V, we do load address into this register T0. Now, we've been seeing like X as our register, RBX as our register. And just remember, register is just memory inside the CPU that's really fast. And is this load D word? Oh, this is load. Yeah, I think this is load D word. Okay. This loads a specific size of word. I forget exactly which size it is. It'll load the size of the word into this temporary register, T1. It'll load value of T0 and it'll add 8 to it. And then it'll load an immediate. Immediate is just this number 2 into 2. It'll compare if they're equal to, and if not, or if they are, they'll jump to label. And if they aren't, it'll go load T1 and the address plus 2 plus 16 bits. All right. That is all for the instruction set architectures, right? You can see that they're all different in their own ways. Like you have to build your own virtual address here. Here, it's relatively simple. A lot of the stuff is consolidated. You don't have to build your own virtual address. You don't have to do a lot of the reloading into registers. You can just, well, it's not visible here, but you don't have to completely load into registers. You can also move something. You can also move the value of a register into a memory address, and you don't have to send that to a register and then write to that, right? So everything isn't built around registers. And then here, you can see it's relatively simple, not bad. Here we did have the virtual addressing, but otherwise it's pretty similar. And these ones all have compares, right? They all have branches. They all have adds. They all have all the basic addition, subtraction, multiplication, division. They all let you add to your memory address, right? So they're really relatively similar, sorry, right? Okay. So that is just, those are some of the instructions that an exe can have, right? But let's talk about how you implement them. And you would implement them through microarchitecture, but let's go to the bottom up. It'll be easier for us to understand from the bottom up, right? Okay. You ever heard that transistor makes up your computer? Well, it does, right? So this is called a CMOS transistor, right? Transistor. So what the transistor does, right, is it lets current through when you give voltage to an input, right? Whenever you give a voltage to an input, and I'll draw that here. So like, I don't know, I'll call this source, drain, and then gate. Whenever you give voltage to the gate, then you can allow electricity to pass, right? And what that does is that it allows you to encode information. Okay. Allows you to encode information. Oh, we'll see about that in a second. But here's the thing, right? Whenever we give voltage in, whenever we give a high value for voltage, what that means is that let's say that I give voltage in as, I don't know, 5 volts, and that 5 volts is enough to let current pass through. We would say I gave a 1 as in, and then output is a 1, right? Well, guess what? There's two different types of CMOS transistors. It's called complementary metal oxide semiconductors, and there's a PMOS and an NMOS, right? Now, what is NMOS? First of all, NMOS says that whenever you want to let electricity through, you have to turn it on, like this. This follows an NMOS structure. And PMOS is the exact opposite. Whenever you give voltage in, the output turns off, and we write that as a 0. Now, they're called complementary because they usually work together in circuits. You really see one without the other in CMOS, right? You can see a more physical version here, and you can see sort of a little bit more proof to that example. This is an NMOS transistor, this is a PMOS transistor, and they're both working together to make to make something. All right. Okay. Now, I talked about encoding information earlier, and let's talk about one specific example of how it can encode information when transistors will work together. That's very useful. Right. Let's say we have two transistors like this, right? So we're given, I don't know, say we're given an input, and then we're input 1 and input 2, right? 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 Input 2, right? See, let's assume these are both NMOS, right? So let's say this one has a value of 1, right? So you can let stuff through, or you can let electricity through, right? Let's say this one has a value of 0, so it's off. So this one is let through, and this one is let off, or not let through, right? So both of these need to be on in order for electricity to pass through all the way, right? That that is very useful in a sequence we'll call later, but you can imagine it. If you imagine this 1 as being a yes, right? It's like, yes, I want electricity to go through. You'd have to have both of these to be yes in order for electricity to pass. That's called an AND structure, right? And that happens when they're both in serial or right next to each other, right? Now, let's say we have them in parallel, right? Pretty sure I'm drawing these wrong. Pretty sure you're supposed to do it like this, but I don't care, right? Okay. We have our voltage in, right? Our voltage in too. Now let's say that this one is high, or 1, sorry, and this one is 0. This one, current will, or not current, sorry, electricity will pass through, but this one won't. So this one will still receive electricity, right? They'll still be there. So here, only one of them, or both of them can be on, and then our output will be 1, right? So this is called an OR structure. It looks like a partial, sorry. Or it's called an AND. And using these together lets you fundamentally build a lot of different things together, which we'll talk about in just a second. Okay. Sorry. Okay. So using these structures together, you can create what is called logic gates. And so a logic gate is just a combination of transistors, right? You can think of it like that. It wouldn't be super hard to think of it like that. But they follow a they follow a certain what's called logic table. And what that means is that whenever you give certain combinations of input, you'll get certain combinations of outputs, right? hmm So doing that, you can manipulate and uh, manipulate and change data, and that can run your computer, right? And you see a couple of these here, not and, NAND, OR, NOR, XOR, and XNOR, right? The main 7 guys, right? Okay. So let's let's just give you an example, right? Let's give you an example. It's called a half adder, right? Now let's just look at a half adder, for example, right? So there's going to be a source carry, and there's in 1 and then in 2, right? Let's assume that. Okay, let's assume 0, 0. Our source and carry is going to be 0, 0, right? In 1, what is this 1 and 0, right? Our source will be 1, or our sum will be 1, sorry, not source. Our carry will be 0. Same here. But what about here if I go both of them? Then we'll get 0, 1. Okay, what is this doing? If you separate these are inputs, these are outputs. Notice how we're adding. Notice how this lets us add in binary, right? It's called a half adder for a reason, right? So lets us add in binary. right? Remember. Or actually, I swapped them. I should have carry and then source on the side. Carry and source, and maybe that'll make it a little bit clearer. Because remember, binary encoding works in the sense that how does binary encoding work? Well, you have a place value, and it can only be a 0 or 1. That's why it's called base 2 encoding, or binary encoding. So if you want to add more data, you'd have to have another place value. So yeah, this is how we add numbers together. Well, let's just look at this for a second, okay? So this is, mm, so S, S only works when we have only one of the inputs is a 1, right? Only one of them is set to yes, right? That's perfect for the XOR gate. You don't know what an XOR gate is, but that is perfect for the XOR gate. We can see XOR. XOR only works when one of the inputs is 1. If both the inputs are 1, or if none of the inputs are 1, it goes 0, right? And then let's look at the carry. If both of our inputs are 1, then we get a 1, and if otherwise nothing, well, that's a perfect example of an AND, right? So we would route our inputs both to an XOR and to an AND gate. And then we'd get, from here, we'd get our sum, and here we'd get our carry. And that's how you make a half adder. So that's how you can use logic gates to make like a thing that does addition, right? And that's how you can modify data. Okay, so a half adder is an example of what's called a combinational logic unit, right? Combinational unit, basically what that means is whenever you give it a signal, they'll start acting on it, right? Whenever you give it a signal, only yeah, it only cares about its current inputs. It doesn't care about anything else, right? So, mhm. So why does that exist? Combinational input. Why does that exist? Well, there's this thing called sequential input. Sequential logic, sorry. Sequential logic works on a timer, right? Every 5, let's say, nanoseconds, you go dung, 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 and on this dung, then our inputs start getting processed, right? Then they start getting processed, then they start doing stuff. hmm And that timer is called the clock, right? So on every what is called clock cycle, then the timer will go off, and then our inputs start getting processed. hmm And the reason we have this sequential unit or sequential logic uh, works in the sense that works in the sense works in the sense no, works. Okay, most sequential logic works on a clock. A latch doesn't work on a clock. Latch, how it works on latch, the outputs influence in the input. What does that mean, right? That means, let's say, for example, that this signal gives you a 1, right? You get a 1, your output will route you to a 1. Will route, will route a 1 over and over and over and over again. And in doing this, you can remember, this logic gate will remember what its signal is, right? hmm And you can see that here, right? It's called a set reset latch. Okay, so you set it with a 1, and it goes and it knots it, and it sends it to 0, and and let's say you reset to 0, then you send it a 1 here. So 1 in, or I think this is an OR, right? I forget. Yeah, 1 or 0 set, or NOR. So set a 0 here, and then this one it gets things 0. Again, no, that's a 0. Yeah, okay. So that's a latch, right? A latch wraps its output to its input so it can remember stuff, right? What is a flip-flop? A flip-flop works on that clock we talked about before, didn't it? Right? It takes input from the clock and it makes sure that your latch only works on that clock by adding additional logic here, right? And you can see even more of a flip-flop. I believe this is a D flip-flop. This is the symbol you might see for D flip-flop, right? Okay. Now, you can combine latches and flip-flops together to create what is called registers. And registers are once again the fastest memory unit in your CPU, or it's in your computer and it's stored in your CPU, right? And then a register file is a collection of registers, right? So you can see it here. We have this register going downwards, going downwards, going downwards, going downwards, right? All of these registers, right?